So, today I will discuss about the magnetic field in a current carrying conductor. So, if current is passed through a conductor, then it produce magnetic field. So, what is the relation between the uh, magnetic field and current, as well as what are the other parameters are involved in the magnitude of magnetic field and direction of the magnetic field, that basically we get from the Biot-Savart law. Okay. So, magnetic field in a current carrying conductor. So, basically Biot-Savart law. So, you know that any current carrying conductor, basically current flowing through a conductor generates magnetic field. The magnetic field at a point due to an element of the conductor carrying current is directly proportional to the current, directly proportional to the length of the conductor element, inversely proportional to the square of the distance r between the conductor element and the point where magnetic field will be detected. Okay. Also, this magnetic field is directly proportional to the sin theta, where theta is the angle between the conductor element and the line joining the element in to the point. Okay. So, this is the Biot-Savart law. So, as per Biot-Savart law, so let me show you. If you take a conductor of any form, if you take a conductor of any form, say this is a xy is a conductor, xy is a conductor, current I is flowing through this conductor. Now, when current flows through a conductor, it generates magnetic field in its surrounding. So, what will be the magnetic field at point O, that we want to find out. So, according to Biot-Savart law, this magnetic field H is proportional to the current, proportional to the current carrying conductor element, this here P q, that this is the conductor. So, we have taken a small part of it. So, say this length is del L. So, that is why we are taking element, okay, small portion of this conductor. So, due to the small portion of this conductor del L, what will be the magnetic field at this point O? So, this magnetic field is proportional to this length of this element, as well as is a proportional to the sin theta, where the theta is the angle between this element and this r is the basically the connecting line between this O, where we want to find out the magnetic field, as well as the middle point of this element. So, this sin theta, theta is, as I told, this is the direction of the, say this element, and this is the direction of the point where we want to find out the magnetic field from this from the middle point of this element. So, this is the angle theta, and magnetic field will be proportional of this sin theta. and inversely proportional to the square of the distance, okay, this r. So, that is what Biot-Savart law. So, proportionality constant say k, and this so h equal to, we can write here basically this proportionality constant k is mu 0 by 4 pi. So, mu 0 is called the permeability or air permeability or permeability of the free space. Okay. So, this one we can write that so we have multiplied with r and divide by r. So, it is r cube and this is r, basically from here I can write this. So, now I dl sin theta r. So, we can take cross product of this dl cross r. So, then because this angle between dl and r, so cross product will give you sin theta. So, we can write dl I dl cross r by r cube. So, this is the vectorial form of Biot-Savart law. So, this is the very important formula for finding out the magnetic field at any point surrounding the current carrying conductor. Okay. So, ideal cross r by r cube and this constant is mu 0 by 4 pi. Okay. So, this now if we find out the current magnetic field in a current carrying circular coil, okay. So, consider the conductors in circular form of radius r. Okay. So, this is the form of the coil, it is a circular form. Now, on the axis of this circular coil, this is the center of the circular coil, and on the axis, if from this point O, if distance is x, okay, at this point say is the point P, at this point say point P, what will be the magnetic field due to the circular this circular current carrying conductor. So, that is what we want to find out. This is the on the axis, off axis also one can find out, but we are interested to find out the current magnetic field on the axis at distance x from the center of the coil. Okay. So, now we will use Biot-Savart law. So, according to Biot-Savart law. So, let us take element of this conductors, this is the small part del L. So, due to this element, okay, so what is the magnetic field here? So, middle point of the element and the point where we want to find out the magnetic field. So, let us connect it. So, this will be actually earlier we in this formula we took r, but here this radius of the circular coil we have taken r. So, this that is why we have taken this that A, right. Now, this is r and this is x. So, A will be, so these are perpendicular, this x and this r is perpendicular. So, A will be this distance between the conductor element and the point where we want to find out the magnetic field. So, this is basically A, and A will be equal to square root of x square plus r square, right. So, your magnetic field at this point will be mu 0 by 4 pi, that is the proportionality constant. I current is flowing this I, okay. So, I dl and this angle between this A and the current carrying element. So, this basically 90 degree, right. So, circular coil and then we are taking this, basically it will be just perpendicular to this OL, okay, current carrying this conductor element. So, this angle is basically 90 degree. So, sin 90 degree divided by the distance square A square. So, from the Biot-Savart law you can find out that these are things, okay. And its direction is basically the perpendicular to the plane of this paper, basically. In this case, okay, I will not take the plane of the paper, because so is this direction of the magnetic field will be perpendicular to the plane which contain the that del L and this A, okay. So, this so that means it is perpendicular to this A, this direction of the magnetic field. So, now it has symmetry, So, you can take element small element on this coil. So, there is a another element just opposite to that, and in this case if you just find out the magnetic field. So, magnitude will be same, but direction will be just opposite to it. So, it will be this way, okay. So, now you see it's it will have basically two component. If this angle is phi, so this will be the phi, So, h cos phi, it is perpendicular to the axis, and another h sin phi, it is parallel to the axis. So, perpendicular to this axis, this h cos phi, and this from just opposite element you will get this h cos phi perpendicular to this axis, they are in opposite direction. So, they will cancel each other, but yes, no, it will not be in this direction, it will not be, I did mistake, it will be basically it will be this perpendicular to this, okay. So, it will be in this direction, okay, just for this element, and yes, it is so h cos phi and h cos phi on for this element. So, they are in opposite direction. So, they will cancel each other, and both will have this horizontal component along the axis h sin phi. So, that will be added. So, ultimately you will get here this magnetic field along the axis, okay, So, that magnetic field is h sin phi equal to I dl, whatever, from here you can find out I dl by a square. So, that is h, and sin phi is basically this r by a. So, r by a I have written. So, you are getting, then now you have to sum up for all these small elements. So, one can integrate also over this. So, it is basically del L, if you sum over this all. So, that will be 2 pi r, circumference, basically 2 pi r. So, if you add it, so that is basically del L I can replace with this 2 pi r. Okay. So, in integration form it is easy to find out, but here it has symmetry, and that is why directly you can replace del L by 2 pi r. So, if you put this one 2 pi r and a value is square root of x square plus r square, then you are getting this, right. So, x square plus r square by to the power half, 3 is there. So, 3 by 2 and this r square. So, 2 pi and 4 pi, this 2 will be there, mu 0 is there, and now here I have multiplied with n. So, is the for a one turn. Okay. If it has n turn, so its length will be, length of this wire will be basically 2 pi r n. So, if number of turns is n, so we have to multiply with this number of turns n. Okay. So, that is the H magnetic field at point P on the axis of this circular coil, on the axis of the circular coil at distance x. So, magnetic field is this and its direction is in the parallel to the axis. So, this is the expression for magnetic field of a current carrying circular coil along the axis on a particular distance x. Now, so if x is 0, that means the magnetic field at the center of the coil. So, if you put x equal to 0, then or then it will be basically this a will be equal to r, a will be equal to r. So, so x equal to 0 or a equal to r. So, at this condition H will be mu 0 I n by 2 r. So, this is the magnetic field at the center of the coil. So, coil have number of turns n. So, here H on the axis as a function of x, H as a function of x on the axis. So, this expression is mu 0 by 4 pi 2 pi n I r square by x square plus r square to the power 3 by 2, and at the center x equal to basically x equal to 0 is x equal to 0, x equal to 0. So, magnetic field is mu 0 by 4 pi 2 pi n I by r. Okay. So, what we want to do? We want to do experiment. We want to do experiment. Using this formula as a working formula. So, what we can study? We can study the magnetic field measuring at different distance from the center, and its how it varies, okay, according to this formula. It's a varying, is almost Gaussian form. It's not Gaussian, but it's similar to Gaussian. Okay. So, that we want to study, as well as we can measure the magnetic field at the center. If we know the current, then one can find out the radius of the circular coil. So, now, circular coil of n turns can be used to produce magnetic field, right, to produce magnetic field. Now, to produce, if you take two circular coil and placed coaxially, then one can produce uniform magnetic field between the two coils under certain condition. If these two coils are identical and they are placed coaxially at a distance, or distance between these two coil, identical coil is equal to the radius of the coil, we tell then it is a Helmholtz coil, and just name Helmholtz coil. Okay. And then between these two coil, if distance are equal to the radius of the coil, then between these two coil will get uniform magnetic field. Okay. So, theoretically you can find out that you will get the uniform magnetic field. So, a pair of coils, that is basically when they are identical and placed coaxially, then we tell Helmholtz coils, right. So, this is the coil. Now, magnetic field will vary like this. Okay. So, from the center if you go this side and if you go other side, so it will vary symmetrically. So, here at the center is maximum field. So, coil 1. So, that what is the field? You have seen that at the center mu 0 by 4 pi 2 pi n I by r. Another coil also, it will give this field variation like this, and this for this say coil 2, and this H 2, this is H 1 I have, okay, fine. So, basically this magnetic field due to this coil will vary like this. Okay. Now, at the center x equal to 0, this is the field. At distance say x at the x equal to r by 2, at distance x equal to r by 2. Okay. R is the radius of the coil. So, what will be the magnetic field? So, mu 0 by 4 pi 2 pi n I, and from this formula if you put in this formula, if you put x equal to r by 2. So, r by 2 means r square by 4, that means 5 by 4, okay, r square. So, to the power 3 by 2. So, you will get r cube, and then 5 by 2 to the power 3 by 2, okay, 3 by 2. So, square root of 125, and 2 cube. So, that is 8, basically 8 by square root of 125 1 by r, okay. And at x equal to r. So, this at x equal to r, at distance from coil 1, for coil 1. So, what is the magnetic field at the center? This, at the x equal to r by 2, this, at the distance x equal to r, this. Similarly, for coil 2, what will be the magnetic field at the center? That is exactly same, sorry, at this point. So, it will be say H 2. So, at this point x equal to, in this case for this coil is x equal to 0 I have to put. So, basically at this point it will be mu 0 whatever field here. So, the same here for this coil 2, at the middle at x equal to r by 2. So, whatever this value, this same value will be for this coil 2, and at x equal to r for this coil 2. So, what will the magnetic field? So, whatever here. So, same field due to this coil 2, because same coil, similar coil. So, now for these two coils, so here you are getting the total field for coil 1 and coil 2. So, this will be the summation of H 1 plus H 2. So, these two will give you 1 by r I have taken. Okay. So, 1 plus 1 by root 8. So, this approximately 4 by this factor is 4 by 3 approximately. So, if you take this root 8, so root 9 if you take is 1 by 3. So, 1 plus 1 by 3, so it is 4 by 3. Okay. Now, at this point if you see, so this will be H 1 is this and H 2 is this. So, just 2 into this one, 2 into this one, okay. This factor will be 2 into 8 by square root of 125, right. So, this is also approximately 4 by 3, and at this point. So, field H 1 plus H 2. So, this it will be same of this one. So, this is the approximately is a 4 by 3. Okay. So, you can see the field when these two coils are placed at distance r, okay, then field between these uh, two center of these coils are same. Okay. So, it is basically you will get, so summation of these two. So, it is you will get uniform field between these two. So, these the so this from Weier's law whatever we got the expression for field using that same. So, we have find out we found that the field for circular coil. Now, for two circular coil placed at a distance r, then this whatever field we are getting, that is giving uniform field. Okay. So, so two coils are used to produce uniform magnetic field in our laboratory. So, this experiment based on this coils, circular coils, is very technologically very important. So, we will do experiment in our laboratory using the circular coils. Okay. So, we want to do experiment in our laboratory, the magnetic field along the axis of a circular coils, this which is carrying current. Okay. So, aim of this experiment is to study the variation of magnetic field along the axis of a circular coil, then find out the radius of the circular coil, then study the variation of magnetic field between two same coaxial circular coils, basically Helmholtz coils, when distance between the centers of the circular coils is equal to the radius of the coils. Okay. So, that is what we want to study in an experiment. So, for that what apparatus you need? You need two circular coils, variable DC current source, Gauss meter with Hall probe, then connecting wires, then we need meter scale to measure the distance. So, this very simple apparatus we need for this experiment. And so, in next class we will demonstrate this experiment in our laboratory, and there what you have to do? You have to so you have to note down the experimental observation. First, as I always tells, you have to find out the least count of your apparatus. So, that is a least count of meter scale. You have to write current source. For current source, what is the least count? For Gauss meter, what is the least count? That you have to note it down. Then for this experiment, just you need one table. So, basically position of the Hall probe or coils versus magnetic field. So, basically you have to measure magnetic field at different distance from the coil center, this for one coil. Okay. And then you have to note down the distance x, and for that what is the magnetic field at that distance, you have to put the Hall probe. Okay. Hall probe is connected to the Gauss meter. So, Gauss meter will give the reading of magnetic field. So, you have to just note down at different distance what is the reading of the Gauss meter, and then you have to plot the graph. If you plot the graph, so you have to take basically symmetrically. So, from the center left side as well as right side, you have to take for different distance, and at different distance what is the magnetic field that you have to plot, and if you plot, then you will see the magnetic field variation is like this. Okay. So, that is what you have to find out, and then you can. So, now at the center what is the value we can find out, and from there you can calculate radius of the coil r. Okay. And now, if you place two coils, okay, and then just you keep the distance between these two at a particular at equal to the radius of the curvature, radius of the coils, and then you just place your Hall probe at different positions between these two coils, and you will see the magnetic field are same. Gauss meter will give you the same reading. That just you note down with for defined distance, and then you tell that you are getting uniform field. Okay. So, and of course, you have to find out the error. So, error calculation you have to perform, then you have to discuss about the experiment and what are the precautions that you have to note down. Okay. So, in next class we will demonstrate this experiment in our laboratory. Okay. So, apart from that we will demonstrate other two experiment. One is the current this force between two long current carrying conductor. Okay. What is the this basically Lorentz force between two current carrying conductor, and using this we will find out the permeability of air permeability one can find out performing the experiment between two straight current carrying conductor. Okay. So, that experiment also will demonstrate, as well as we will demonstrate the inductance when instead of DC current, if you just pass AC current in a coil. So, then and if you put another coil near to it, then this in second coil the magnetic flux will change with time because of this AC current means AC magnetic field in the coil 1. So, then when variation of magnetic field or variation of flux in a coil or in the second coil, then inductance, self inductance if just for a particular one coils, okay, and mutual inductance, that is on the second coil due to the variation of magnetic field in the first coil. So, this mutual inductance basically that experiment also will demonstrate in the laboratory in the successive classes. Okay. So, these are very important experiment in the sense that in laboratory for electromagnet we use this principle to produce magnetic field. Okay. So, these the experiment which will demonstrate how to produce magnetic field in a laboratory. So, that is what we are going to perform in next class in our laboratory. So, thank you for your kind attention.